Going to do section 4.3, acid-base reactions. First, we're going to start with some general background information on acids and bases. So, some properties of acids. So, I put up some different properties. They taste sour. They can change the color of a plant dye. An example of this is hydrangeas. Depending on whether the soil that a hydrangea is growing in, the actual flowers can be either pink or blue. Acids can also react with some metals to form hydrogen gas. There's a few other properties that are listed in your book, but we're not going to worry about those. And then we're going to move on to properties of some bases. Bases feel slippery. An example of a feeling slippery would be soap. Bases taste bitter. And they can also change the color of some plant dyes. Again, the hydrangeas, depending on whether the soil is acidic or basic, the hydrangeas will be either pink or blue. All right, now we're going to learn about, there it is, Bronsted-Lowry acid-base definition. The definition of an acid in the Bronsted-Lowry definition is that acids donate protons. Bases accept protons. Now a proton is just an H+. If you think about it, hydrogen has one proton and one electron. If you take off the electron, you have just a proton. If you take off an electron from the hydrogen atom, you're left with just a proton, which would be H1+. This leads to the concept of a conjugate acid-base pair. We only talk about conjugate acid-base pairs with regard to Bronsted-Lowry acids and bases. So the acid of a conjugate acid-base pair has one extra H+ compared to the base. So I've got a little chart here. And I'm going to work the first few problems with you, and then I'm going to have you pause and see if you can figure out how to fill in the rest. So, HClO would be hypochlorous acid. Now, our definition says the acid has one extra H+ compared to the base. So to get the base, we're going to take away an H and take away 1 from the charge because we're taking off an H+. So we will be left with ClO. And we also have to take away 1 from the charge, so we have ClO1-. To go from the base to the acid, we're going to have to add an H+, because the acid has one extra H+ compared to the base. So if I have NO2-, I need to add an H+. I will end up with HNO2, and I have to add 1 to the charge. So I'll have HNO2 with no charge. HCO3 to get the conjugate. Oh, and if you want to just stop and fill in the rest, you're welcome to do that. If you still need a little more guidance, just keep listening, but it's fine to pause, fill in the rest, and then move forward on the video. Okay, HCO3- base. We need to add an H+ in order to get the acid. So we will have H2CO3, we added an H, and we also add 1 to the charge, so this minus becomes a 0, and we have just H2CO3. All right, H2PO4, we're starting with the acid. To get the conjugate base, we need to take off an H+, so we have HPO4, we took off the H. We also need to take away 1 from the charge, so the -1 becomes, that's right, a -2. Okay, HPO4, 3-. As a base, what do I need to do to make it an acid? Yes, I need to add an H+ to it. So, what will my final answer be? Hopefully you got it. HPO4, 2-, because we added 1 to the charge. All right, we're going to move on to discuss reactions involving acids and bases. We've learned a little bit about acids and bases, and now we're going to do reactions. We're going to learn how to predict products, getting at ionic equations, but we're going to start simple. All right, so the reactions we're going to look at in this class will just be double displacement, like precipitation reactions. We are going to exchange the H plus in the acid with the cation in the base. All right, so we'll start with an example. We're going to just predict products and balance. Right now, we do them exactly like we did the precipitation reactions. The first step is to figure out your charges. Na is +1, hydroxide is -1, H is a +1 charge. Hopefully you recognize SO4 sulfate, -2 charge. We switch the H plus with the cation, so H plus will go with OH minus. Notice I did not carry the subscript for the H over to the other side. The same exact thing that we do with precipitation reactions. We don't carry the subscripts over to the product side unless they are part of a polyatomic ion. All right, where are we? Oh, sodium. What's the sodium ion going to go with? That's right, the sulfate ion. Now, we have to make sure that our charges add up to 0. Does plus and negative add to 0? Yes, it does. Okay, over here, now, what subscript do I need on the sodium in order to make this whole chemical compound have a 0 total charge? Hopefully you figured it out. Yep, there's a 2 there. Okay, we've predicted our products. And once we predict our products, we then have to balance the overall chemical reaction. We do that with coefficients. So first I'm going to check my NAs. I've got 1 on the left, 2 on the right. We put a 2 in front of the NaOH. Let's check our hydroxides. Let's delete that. Okay. We have 2 hydroxides on the left. Now where is our hydroxide over on the right side? Oh, right over here, this HOH. You may recognize that's actually just water, but for now we're going to leave it as HOH because it's much easier to balance this reaction if I think of the OH on the left and the OH on the right as just being hydroxide for now. So notice I have 2 hydroxides on the left, so I'm going to need to put a 2 in front of my hydroxide, in front of the whole HOH on the right side. Let's check our H's now. Okay, notice I have 2 H's, but I also seem to have some H's over here, except I already balanced those with my hydroxide, so I don't need to worry about these H's in the sodium hydroxide or these H's over here with the OH. So I have H2, 2 H's, and note I have 2 H's right here. We're good. How about the sulfates? 1 SO4 here, 1 SO4 here. This chemical is indeed balanced. Okay, I just said this chemical is indeed balanced. Actually, it's the reaction is balanced. We balanced the reaction. Okay, number 2. And note, we're not doing the ionic and net ionic yet. We're going to do that in a few moments because there's a little bit, it's a little more tricky than what we've learned so far. It's not actually more tricky, you just have to know a few more things. For now, we're just going to get to the molecular equation. So, we've got our 2 products. We need to figure out our charges. Barium is in the +2 column. Hydroxide has a -1 charge. H has a +1 charge. PO4, what's the charge on a phosphate? Hopefully you got it. -3. Okay. Switch the positives and the negatives. So the barium +2 goes with the PO4 -3. And the H +1 goes with the OH -1. Okay, what's the next step? That's right, we have to balance our charges to make sure that the whole chemical can add up to 0. Did any of you make a mistake where you carried your subscripts over to the right side? If you made that mistake, check right now to ensure that you didn't carry this 2 over to the right side and you didn't carry the 3 from the phosphoric acid over to the right side. We just bring single ions over to the right side where the products are. Okay, back to balancing this barium with the phosphate. Have you figured out what your formula needs to be? Those 2's and 3's, it always gives you a problem. You have to make the total balance to 6. So we're ultimately going to need 3 bariums and how many? That's right, 2 phosphates. This 3 on the barium doesn't look very good, so we're going to try to fix that. I know we're having some issues with my handwriting. We'll pause this for a moment and fix that 3. Shoot, was that recording? What? I don't think it was recording. Oh, it's recording right. Okay, I know there were a few seconds in there of confusion on my part. Sorry about that. I thought I hit pause and it did not pause, so it was still recording. I apologize. I was trying to fix the 3 on the barium. Okay, that's going to happen in the beginning. I don't have tools to edit out parts of the video. If I get those tools ever, I promise I will get rid of those extra little bits that aren't necessary. Okay, we were on balancing the chemicals. So H and OH, is that balanced? Yes. Plus 1 minus 1 adds to 0. What's our next step? That's right. We need to balance the overall reaction with our coefficients. So let's check what we have. 1 barium. How many here? 3. So what do I need in front of my barium hydroxide? That's right. I need a 3 in front of my barium hydroxide. Okay, here's a little bit of a tricky one. How many hydroxides do I have here? Hopefully you've got this figured out. It's 6. We need 6 hydroxides on the left because we have our 2 times 3 gives us 6 hydroxides. And over on the right side, here's our hydroxides. We need to put the 6 in front of the HOH, which indeed is water. Moving on. We have our H's. We have 3 H's over here. But now on the right side, just H's by themselves, I have 6. So what do I need to put in front of the H3PO4? That's right. I need to put a 2. Let's check our barium. Oh, we already checked our bariums. Let's check the phosphate. I've got how many? Not 1. That's right. I've got 2 on the left side, and I have 2 on the right side. This indeed is balanced. Okay, we're going to move on to ionic and net ionic equations. One thing that you have to know when you are dealing with ionic and net ionic equations for acid-base reactions is that strong acids split apart. We learned that in lecture the other day. Soluble ionic compounds and strong acids are the only things that split apart in our molecular equations. Any acid that's not strong is weak. And remember, for this class, acids will be things that the formula begins with H. There are acids in your book, such as acetic acid. Some people call it methanoic acid. And for your book, that is written with the H at the end. So sometimes you will see the H written at the very right side of a chemical. Okay. So if we are going to learn that strong acids split apart, we better know what acids are strong. We have a little song. It goes, it's not a song, it's a little saying. If you can memorize this saying, you'll be good. If you can't, you just have to memorize these strong acids. And it goes like this. Hibber, hickel, high, hono, hickel, low, H2SO4. I don't know if you caught that. We just say Hibber, hickel, high. We're just reading left to right. Hibber, hickel, high. Hano, hickel, low is the HiO4 and the HClO4, H2SO4. Now, in some places, you will also see that HClO3 is considered a strong acid. I'm not going to give you that one on any problems for any of our exams. Okay, so let's start with number 1 above. We're going to determine the ionic and non-ionic equations. First for number 1. So I've rewritten number 1 that we already did. This is the molecular equation. You'll notice over here on this HOH, I left it as HOH. I know it's H2O. I left it as HOH just so that we could see that water is actually made up of an H plus and an OH minus. It's completely okay to write H2O. In many ways, it's more correct to write H2O, but I'm doing this for emphasis. Okay, when we are figuring out what to split and what not to split, we have to check if something is a soluble ionic compound or a strong acid. So, sodium. Sodium, anything with an alkali metal is soluble, so we are going to put AQ for aqueous. And because we put AQ for aqueous, we are going to split that apart. Next thing, we have to recognize that H2SO4 is an acid. Then we check, is it one of our strong acids? Yep, it is. It's right over here, H2SO4. This is a strong acid, and we are told that we have to split apart strong acids. Typically, you will write AQ for, there's Dylan, for acids, because acids actually are aqueous. They are dissolved in water. But AQ doesn't necessarily mean does not split apart, because if we have a strong acid, which would be aqueous, it will split apart. Now, HOH. It is not a soluble ionic compound. It is not a strong acid. Therefore, it is going to come straight down. And now we're going to have a new little subscript here. HOH is water, which is a liquid. We're forming a liquid there. That's going to come straight down because it does not split apart. Next chemical, sodium sulfate. Well, it's got sodium, our alkali metal, and we know that alkali metals are always soluble. So we know that this chemical is going to be a soluble ionic compound. We're going to write AQ, and we're going to split this apart. So now we're going to work on splitting all of our chemicals that split into their ions. We're going to have 2 Na plus and 2 hydroxides. We're going to have 2 H pluses, 1 SO4, 2 minus. Remember, when something splits apart, you have to include the charge. Subscripts, if they're not part of a polyatomic ion, get multiplied by coefficients. So the 2 in the H2SO4 is going to get multiplied by the coefficient of 1, and that will become 2H plus. The 2 waters, now I'm going to write it as water. The 2 HOHs, they stay together. The Na2SO4, this 2 on the Na2SO4 becomes a coefficient. And this split apart, so I have to include the charge. SO4, 2 minus. Right, that is my ionic equation. And from here, I have to figure out what my net ionic equation is. So I have to identify who are my spectator ions. So everybody take a look. Have you figured it out? All right, nicely done. It's the sodiums and the sulfates. So the sodiums and the sulfates, they did not change at all. They are just spectating. Those are our spectator ions. Okay, so our net ionic equation is going to just be 2 hydroxides, 2 hydrogens, make 2 waters. I can simplify this. Do you notice that we have 2's common factor in every coefficient? So we simplify this and we just write H plus and OH minus makes H2O. And there is my net ionic equation. And we're going to move on to do number 2 now. Okay, I've rewritten number 2. And what's our first step? That's right, we've got to figure out if anything's a soluble ionic compound or a strong acid. So first we'll look up our barium hydroxide, and we find hydroxides are insoluble except with alkali metals, barium ions, strontium ions, and calcium ions. So actually this chemical is indeed soluble, so we will write AQ because it's a soluble ionic compound. Now H3PO4, we've got an H here, so we know that this is an acid. Let's check if it's one of our strong acids. We'll look back up at our list of acids. H3PO4 is not up here. Therefore, it's not a strong acid. Acids, I always write AQ, but this is actually a weak acid, and since this is a weak acid, we're not going to ultimately split it apart. So this one is going to come straight down while the barium hydroxide is going to split apart. Now we're going to check the barium phosphate. And we have a rule about phosphates. Phosphates are generally insoluble, and barium is not one of the exceptions. Therefore, this chemical is going to form a solid. HOH, that's our water. Is it a strong acid? In case you're not sure, you can always check your list of strong acids. It's definitely not there. Water is not a strong acid. We would have major problems in life if water was a strong acid. And now, is it a soluble ionic compound? Of course not. No way. It's not even ionic. We don't have any metals in there. So we have water, which is our liquid, and liquids come straight down. Solids come straight down. Oh, this is an interesting one. It looks like there's a lot of stuff coming straight down, not too much to split apart. So let's do our splitting apart here. Let's see, with our barium hydroxide, we're going to have 3 bariums. Don't forget, when you split things apart, you have to include the charges of the ions. How many hydroxides are we going to have? Notice there's a coefficient of 3 and a subscript of 2. Hopefully you figured out there's going to be 6 hydroxides. Okay, the phosphoric acid, we don't split it apart. Just H3PO4. The barium phosphate, we do not split that apart. Come straight down. And our 6 waters, we do not split apart. Come straight down. Now we check. Are there any spectator ions in here? Are there? Hopefully you're seeing there are absolutely no spectator ions. In this case, our ionic and net ionic equations are actually the same. Okay, so here is our completed ionic, and it turns out our net ionic equation for number 2. Let's move on, and you're going to get a flash of everything, and I'm going to cover this up. Okay. Very last thing in this section is learning about mono, di, and triprotic acids. So hopefully mono, you know, means 1, di means 2, and tri means 3. Protic, remember a proton is an H+, so protic would be how many H pluses there are in the acid. The words are just, they make sense with the meanings. So mono would have 1 H+, di would have 2 H+, and tri would have 3 H+. And here are examples of mono, di, and triprotic acids. So note the monoprotic acids have 1 H, the diprotics have 2 H's, and the triprotic has 3. And that concludes section 4.3.